Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next few weeks, I will be releasing a sample free response question for each of the 4 AP Physics exams to demonstrate to students what kinds of questions will be asked and how the AP exam will ask them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the opportunity to work with released exam materials prior to exam day, and this video series is primarily intended to help those students. AP Central has this to say about the free response questions on the AP Physics C Electricity and Magnetism exam. There will be one question on experimental design or with a lab-based component. And then the 3 questions on the whole will assess all 7 of the science practices listed here. This video will focus on the C Electricity and Magnetism exam from 2018, question number 1, which involved Gauss's law and electric potential. A solid plastic sphere of radius A and a conducting spherical shell of inner radius B and outer radius C are shown in the figure above. The shell has an unknown charge. The solid plastic sphere has a charge per unit volume given by rho of R equals beta times R, where beta is a positive constant and R is the distance from the center of the sphere. Express your answers to parts A, B, and C in terms of beta, R, A, and physical constants as appropriate. Part A. Consider a Gaussian sphere of radius r concentric with the plastic sphere. Derive an expression for the charge enclosed by the Gaussian sphere for the following regions. So for r less than a in part excuse me, in part 1 here, we are talking about here's our inner part of radius A, and we are talking about a Gaussian sphere that is somewhere inside. So we are not enclosing the entirety of the that inner sphere. We need some portion of its volume. And that's something that's going to be a critical part of answering this question. Okay, that's a little slightly better drawn radius there, or a circle there, to show our Gaussian sphere. So we need an expression for how much of the volume of the sphere has been enclosed, because that's what portion of the charge that's on the sphere will be enclosed by our Gaussian sphere. So here we go. So our charge enclosed is going to be equal to the integral of rho dV, which is equal to the integral of beta, what am I talking about? Beta r dV, because beta times r was the function for rho. So now we're going to look at the fact that we need to replace that dV with our proper variable for integration, which is r. So dV is going to become 4 pi r squared. I'm using capital R here, times beta times capital R, d capital R, and this is of course because little r was meaning the radius of our Gaussian surface, so I needed a different variable. So yeah, our differential little piece of volume is equal to the surface area of the enclosing sphere multiplied by dr. So our next step here is going to have us pull out some constants. 4 times beta times pi times the integral of capital R equals 0 to capital R, our variable of integration, equals little r, the radius of the Gaussian sphere, equals capital R cubed d capital R. Oh my goodness. And then that's going to give us, when we evaluate it, it's going to give us 4 beta pi times r to the 4th over 4, which we will evaluate from 0 to little r, and we are going to get an expression for the enclosed charge of beta pi times little r to the 4th. So let's talk about scoring for this part, where we're going to get a point for using an integral to determine the charge enclosed. We are going to get a point for substituting dV into the integration to determine the charge enclosed. And then we're going to get our final point here for the correct answer. All right, and for radii that are in between the sphere and the plastic shell, so for radii between A and B, well, this is actually quite simple. The charge enclosed is just from the charge on the sphere, so beta pi A, the radius of the sphere, to the 4th. And we're going to get a point here for an answer consistent with A part 1. And this is a really common way that the AP exams score. That if you get an answer wrong, but you use it correctly in a subsequent part, you're only penalized once. So if you had a wrong answer but for part 1, but you used it correctly for part 2, you could still get full credit for part 2. Part B, use Gauss's law to derive an expression for the magnitude of the electric field in the following regions. So for R less than A, okay, so we are looking at Q enclosed over epsilon naught is equal to the integral over the closed surface of the electric field dot dA. Well, we're going to have some, our charge is going to be some function of R, the radius of our Gaussian sphere, because as we showed in the previous part, we're only going to encompass a portion of the volume of the sphere. So Q of R over epsilon naught equals the electric field times the area of a sphere, which is simply going to be 4 pi times r squared. So our charge is a function of r. We just saw in the previous part, beta pi times r to the fourth divided by epsilon naught. And that gives us equals E times 4 pi r squared. So our final answer here for the electric field is going to be beta r squared divided by 4 epsilon naught. And for our scoring, we're going to have a point for substitution of the area of the Gaussian sphere into Gauss's law. And then we will get a point for substituting our charge from part A1. Now we're going to use Gauss's law to derive an expression for the magnitude of the electric field in the region between the sphere and the plastic shell. Well, I'm not going to show you the, first couple steps of applying Gauss's law because we just did that on the previous slide. But what I will go ahead and jump to is that step where we substituted for Q as a function of R, because A part 2, we found it to be beta pi a to the fourth. So we'll put that over epsilon naught equals E times, again, that area of the sphere, 4 pi r squared. So I'm going to get an electric field strength here equal to beta a to the fourth divided by 4 epsilon naught times r squared. And this one was worth only 1 point for substituting the charge from part A2 into Gauss's law. Part C. At any point outside the conducting shell, it is observed that the magnitude of the electric field is 0. So part 1, determine the charge on the inner surface of the conducting shell and justify your answer. So let me grab my pen tool. So here's what we know, that the electric field for the shell is equal to 0. And according to Gauss's law, that has to be equal to the charge enclosed divided by epsilon naught. And so we know that the net charge enclosed has to be equal to 0, which means that the charge on the sphere has to be plus the charge on the inner surface of the shell, have to add up to 0. So what that tells me then is that the charge on the inner surface of the shell is equal to the opposite of the charge on the sphere. And the charge on the sphere was beta pi a to the fourth. So the charge on the inner surface of the shell will be negative beta pi a to the fourth. And so notice something that I did here. I actually did the justify my answer part to handle all of the thinking through all the steps before I actually you know, made a statement of the charge on the inner surface of the shell. So that is one of my pro tips for how to answer questions like this. Determine the charge on the outer surface of the conducting. Oh, I actually should talk about scoring. Sorry, let me do scoring really quickly. We are going to have an answer. I put my answer last, of course. An answer consistent with part A2. And it must have the opposite sign. And in fact, that is important enough. I'm going to change colors. Because of course, the positive shell, the positive charge on the sphere is going to attract negative charge to the inner edge of the shell. And our second point here is going to be for the correct justification. Here we go. So and then determine the charge on the outer surface of the conducting shell. That is going to be, I'll call it Q outer, is equal to 0. And we get just 1 point for the correct answer on this. Part D, on the axes below, sketch the electric field E as a function of distance r from the center of the sphere. Sketch the graph for the range r equals 0 at the center of the sphere to r equals c at the outside of the conducting shell. So we saw our previous relationship had, something that dealt with r squared. So we have this, concave upward curve from 0 to A. And then we're going to have a decrease, also concave upward from A to B. And then the electric field outside the shell is going to drop to 0. So let's talk about scoring. All right, so we're going to get a point for a concave upward graph that begins at the origin and increases to r equals A. We're going to get a second point, and I just lost, oh, there it is. I lost track of my cursor. It usually happens like at least once a video, and especially when it's paler like this orange, it's really easy to lose. So we're going to get a second point for a concave up graph. That is continuous with the first section. And decreases from r equals A. R equals A. Don't know why my Brain decided that should be less than. 2. I was thinking about writing 2R equals B, and I started to write Tor. Okay. Yeah. I'm just going to leave it. It looks like a sigma. To a non-zero value at B. That is important. That our electric field does not drop to 0 until we are outside the shell. And then our final point is going to be for a graph with a value of E equals 0. For R greater than B. And there is a note that due to the scale of what you are drawing, that the discontinuity at B is not required to be shown. So it's okay if you just showed electric field equals 0 for points beyond B without that drop, but you can't have the electric field at R equals B equal to 0. And part 2, the figure below shows the sphere and shell with 4 points labeled W, X, Y, and Z. Point W is at the center of the sphere, and point X is on the surface of the sphere, and points Y and Z are on the inner and outer surface of the shell, respectively. Rank the points according to the electric potential at that point, with 1 indicating the largest electric potential. And if 2 points have the same electric potential, give them the same numerical ranking. So our potential is going to be strongest at point W inside the sphere. X on the surface of the sphere will be next. And then Y and Z will have equal electric potentials being on the shell. And so we have 4 points. We're going to have any ranking that has Y and Z at the same potential. And another point for ranking the electric potential. Look a little bit better. With W greater than X greater than Y and Z. So I hope you have found this demonstration of an AP Physics C electricity and magnetism exam question helpful. If you have a video solution you would like to request from my YouTube channel, you can send it to physicsproblemrequest@gmail.com. If you need some email assistance, you can message me at freephysicshelpline@gmail.com. Please send your question and the work you've done on it so far, and there's a limit of 10 questions per academic year. If you'd like to learn more about my online physics tutoring services, you can reach me at brandyhefflinphysics@gmail.com. You can visit my website at virtualphysicsofficehours.com, and you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics C Electricity and Magnetism exam, and those materials include the release free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these released exams live, and to see what the scores for that year were looking for and how they decided to award points. If you have questions, you can reach me at brandyheflinphysics@gmail.com. I'm physics tutor Brandy. I love physics, and I love helping you. Until next time.